slide. Hummocky topography. One of the things that also affects why your superficial geology doesn't always reflect what your recharge rates are in groundwater flow models is looking at dead-end storage and these closed depressions and hummocky topography up on moraines in particular. And this is just some mapping, and this was a study that the M&R did for us a number of years ago now. But when you see these joints at different map sheets, and in this case, the geologist who did the mapping called this a hummocky terrain, and in this case, he didn't. And we had the M&R do some, next slide, do some work for us in terms of trying to tease out a consistent methodology of looking at hummocky topography. And so they took the DEM, the digital elevation model, the ground surface, and basically tried to fill it up with water. And where you don't have drainage away from a property, you can see that the water fills these closed depressions to a certain level. I mean, if they kept putting water on, it would finally drain. But there's a number of closed depressions, and of course these closed depressions tend to promote recharge into the ground. So these areas, you would not bump the recharge up if you were doing groundwater flow modeling. And the next slide, similar kind of case where you have, in this case, very hummocky topography, but very few closed depressions. But in this case, the flow paths across the surface would be very tortuous, and the soils, again, on the moraines are very coarse-grained, so in areas like this, you would also tend to bump up your recharge, given what you know about the geology and the sediments on the surface. And then moving to the new era of trying to integrate groundwater, surface water together. This is just one example, but this precipitation recharge modeling system that's coming out of the USGS, they're linking it to our groundwater flow models and really trying to look at climate data and radiation data and take a look at how much water is trapped in the unsaturated zone and how much winds up moving down to recharge the groundwater flow system. And there's a whole bunch of different processes that you add on, and complexity, of course, as you go in this direction. And at the end of the day, I mean, even these models really, the PRMS, I mean, we're doing some work right now to try and look at how much further it takes you in terms of understanding your groundwater flow system. And really, you see from our original groundwater flow model versus the new and improved, linked surface water, groundwater estimations. I mean, you see some very similar patterns in terms of recharge, and again, it really reflects the superficial geology. And so we're still, I guess, just evaluating. I mean, these models. The great thing about the PRMS is that it tells you the timing of when your recharge occurs. So if you're inputting your radiation, your climate data, and your temperature, and so on, you can start to see when your snowpack melts, when you would get your recharge, and when, if you had drought scenarios and so on, then you can start to play with the timing and then take a look at all that. But from a steady state, really trying to understand your groundwater flow system and look at how groundwater is moving, it doesn't look like, from that point of view, they really give you a big advantage. But again, we're still doing some work to look at this. So then, I mean, just some of the things that you have to think about when you're, I started thinking about significant recharge areas. So this is a piece that you guys have to do for the assessment reports, is delineate these significant recharge areas. And we have a project with M&R and MOE right now, trying to do 3 universities to take a look at this over the next year. So it's an area of active research that the province is still looking for direction on. But some of the things that I think you have to think about is, when you're talking about recharge, you just want to look at the spatial areas of where you think you were getting recharged. Do you want to quantitatively calculate your recharge for water budget purposes? So I think you have to think about what you're trying to do. And secondly, the scale of your analysis, and all of these things is very important. And I think you have to be cognizant, if you're looking at watershed, sub-watershed, or local scale, and what sort of information is required for that. So I guess, given the complexity of trying to measure recharge, there's a whole bunch of different ways that hydrogeologists and then surface water folks try to kind of guesstimate or hone in on recharge rates. One is just by looking at base flow measurements. So conservation authorities for the last number of years have been out measuring stream flows, usually in the summer. And what you can do with those stream flows, even though they're one-time snapshots of flow, you can take a look at the stream and say what's your flow per unit area. And in a map like this, the dark areas have much more flow than the light-colored areas. So you go to those streams, and they're pouring out the water. So you know that there's something unique about those areas. And one, maybe there's a higher recharge rate into those catchments. Two, maybe there's groundwater flow that's crossing surface water divides. So maps like this, I mean, this is a really effective way, by just going out and measuring base flows, to try and conceptually start to understand your subsurface and how the water's moving below us. So really, really good tools. And then, so if you assume, the other thing that you could do is when you've got flow gauges. So this is just an example, the Holland River. I should mention a lot of this work too is being done by my colleague, Dr. McGerber. He's adjunct prof at U of T, and he's working on the same project with me, and he's done a lot of work. So should give him credit for some of these slides that are coming up here. But if you have a flow gauge, so this is more than just spot flow measurements on a one-time basis, you can really start to tease a lot of information out of your surface water flow gauge. So in the case of the Holland River, we've got a gauge here, and you can make it in Ontario. Often is true. It depends where the gauge is located. But if you have a gauge at the bottom end of your watershed, quite often, because we don't have the topography in Ontario to drive really deep groundwater flow systems, quite often our flow systems are quite shallow, and your active groundwater flow systems are moving the groundwater from the subsurface to the surface. And you could assume, in many cases, I mean, when you look at the data, you can see if your assumptions are valid. You can assume that all the water that's going into the ground comes out above your gauge. And you take a look at your base flow measurements from the gauge and compare them to your recharge estimates, and you can start to get a handle on teasing out your recharge rates. So next slide, this is the kind of thing you would do. You take your flow gauge, you have your measurements here, and the spikiness is the real measurement from the flow gauge. And what you try to do is do this base flow separation. And there's a whole bunch of techniques, but basically you're trying to shave off these peaks, which are related to surface water rainfall events, and really try to get the groundwater component that's feeding your stream. And the important thing is that this groundwater component is not consistent. I mean, there's a lot of misunderstanding like this in terms of base flow, that people think it's consistent the whole year. But the groundwater flow system, can be up and down by several meters, and as it comes up, your base flow discharge to streams would increase. As it goes down, your base flow contribution to the streams would decrease. So anyway, what you're trying to do is take the groundwater component of your stream flow and say, okay, that's the quantity of water I've got to work with. And next slide. Here for one of these flow gauges, you can see this is the kind of analysis that we would do. Is you have your precipitation, how much precip's over 800 millimeters a year falling on the watershed. How much is flowing in the stream? About 200 millimeters. That's the flow gauge. Then we take the separation. We said, okay, how much is base flow? How much is groundwater that's coming into the stream? So you do that analysis I showed you on the previous graph. And you end up with a base flow measurement. And so you can start to look at these numbers and try to make some sense of whether the recharge. So in this case, we would say, oh yeah, the recharge estimate is maybe about 100 millimeters a year is recharge, or 120, 130 is maybe going into the subsurface. A lot of the difference between these two would be the runoff, and you start to think about your watershed and where your gauge is. I mean, I forgot to point out in the cross section, but you could get, in this case, you could get a lot of groundwater bypassing your gauge, because our flow gauge in this case is somewhat up from Lake Simcoe. So again, just trying to really understand the system and understand what you're measuring and how to use the data correctly.